Welcome to this tutorial about how to perform a Pearson correlation in Jamovi, and we'll also look at how to do the non-parametric Spearmen's correlation. But first, we'll look at the example data that we're going to be working with in today's video. What we have here are two variables that have been recorded from a sample of 25 participants. This first variable is an individual's forearm circumference. So what we did is we took a tape measure and we wrapped it around the largest part of an individual's forearm and recorded the circumference of that, and that's going to be our estimate of muscle size in the forearm. The second variable we then recorded from each participant was hand grip strength. So squeeze the hand grip dynamometer as hard as we can and record that in kilograms, and then we can essentially see the relationship between muscle size and muscle strength. So we did this in 25 participants, and each participant has a recording of forearm circumference and hand grip strength. Now what we need to do is firstly check the assumptions of this data to ensure that a Pearson's correlation is appropriate. So I'm going to bring up the assumptions here. We've got four assumptions that we need to check. Assumption number one being that our two variables, so forearm circumference and hand grip strength, are measured at the interval or ratio level, and they are essentially continuous. We can see that it's forearm circumference measured in centimeters. That is a continuous, that is a ratio measurement, and the same with hand grip strength. That is also a ratio measurement. So that's just your knowledge of what type of data each variable is. In this case, we've satisfied that assumption, so that's all good. Then we need to check if there's a linear relationship between our two variables. And we can very simply do this by firstly plotting the data. So we're going to come up to Jamovi and hit plots, and what we want to plot is called a scatter plot. It doesn't matter which way around we plot the data, so you can move any to the x-axis and then move the other to the y-axis, and that will immediately generate the scatter plot here. We really don't need to do anything else here apart from look at the data and sort of see what the pattern of it looks like. Is it a linear relationship here? Well, yes, we can see that if we was to draw a line of best fit, it would come somewhere along through here like this. There's no clear bend in the data as the values change. So we can be happy with that. We then need to check if there's any significant outliers, which we can also refer to this scatter plot here. So is there any data points which are very far away from the spread? This one looks like it might be a little bit, but I would be happy with that to say that it is not a major outlier. So it's not something that's like up in this top left corner here. This is okay, and it's not a clear and obvious outlier here. Therefore, we've satisfied that assumption that there's no significant outliers. And finally, we need to check if our variables are approximately normally distributed. The way we do that in Jamovi is by coming to Data or Analyses and going to Exploration and going to Descriptives. And we want to check the normality of each of our variables. So we're going to drag both forearm circumference and hand grip strength across to our variables, and then we're going to come down and go to statistics, and we're then going to check the normality Shapiro-Wilk test. We're going to come down to plots and then also check the box plot, and we'll get the Q to Q plot. So we can see that with the descriptives, it gives us the Shapiro-Wilk p-value for each variable that we've got. So for forearm circumference and hand grip strength, we can see that both of these variables are above 0.05. So therefore, we can assume normality for each of our variables here. If we look quickly at the box plots, we can see that we've got no outliers. And then we can look at the Q to Q plots for each variable just to confirm that it looks normally distributed from a more qualitative sort of way. And we can see both of those variables follow the line like it should in the Q-to-Q plot. So we're fairly confident there that we have no outliers and we have normally distributed data, which means that we have satisfied that fourth assumption, and we can now actually run the test. So I'm going to scroll down to the bottom of our output window, and now I'm going to go to actually run the Pearson's correlation. This is going to be under the regressions area within the analysis tab. So we're going to click on regressions, and what we want to do is we want to go to correlation matrix. And it's called a correlation matrix because there might be cases where we want to correlate multiple variables. We might have 10 variables that we might want to all plot against each other. And you can essentially do this in Jamovi by doing a correlation matrix. So it's a very streamlined way to do multiple correlations at once. In our case, we've only got 2 variables, so it's only going to show up as one correlation. And it's a simple configuration where we drag across forearm circumference and we drag across hand grip strength. That will immediately do the analysis here. We don't actually need to change anything else by default. So we have the parametric test selected by default, the Pearson's correlation. The hypothesis for the p-value is a two-tailed hypothesis in the way that we're looking for both positive and negative correlations, so we leave that by default. You don't really want to select a one-tailed test because it can actually hide any potential negative relationships when you thought you had a positive relationship, and vice versa. We're going to report significance if you really want to. This is not going to make much of a difference for just a single correlation, but you can flag significant correlations. So if you have lots and lots of correlations, it's going to put these little asterisks next to it so you can quickly see which correlations are significant. We're not going to bother about the 95% confidence interval now, but you may also want to then plot a correlation matrix, which is going to be fairly similar to the previous plot that we looked to check the assumptions. But I like the one that we just did more because it's larger and you can see it easier. So let's look at the actual test itself. So the first thing we need to do is to double check that correlation scatter plot, make sure we do have that linearity and make sure that we don't have those outliers. So that's fine. The second thing we need to do is check the p-value before we check the Pearson's R. So we can see the p-value for this correlation is less than 0.001. That value is lower than 0.05, which is our alpha level that we use for our statistical tests in common practice. Therefore, we have a highly significant correlation here between hand grip strength and forearm circumference. So now that we know it's a significant correlation, we interpret the R value. And we can see that it's a positive value, so it is a positive correlation, and the correlation coefficient is 0.811. So we need to now benchmark that against our interpretations that we had in the lecture slides here. So 0.81 is in the bracket of the very strong correlation here between 0.8 and 1. So we have a very strong positive correlation. That's it for the analysis. Now we just need to write this up into our results. So here is the standard way that we would report this. So we need to firstly figure out if we rejected or failed to reject the null. Well, based on our p-value being less than 0.05, we're going to reject the null hypothesis, so we don't need to use this template. We're going to use this template. I'm going to delete that because that's not going to be actually relevant for our results reporting. So we just need to fill out the red components. So Pearson's correlation revealed a very strong, because it was 0.811, above 0.8. It was a positive relationship because it was a positive number, so I'm going to delete that and say positive. Relationship between hand grip strength, that's one of our variables, and our other variable is forearm circumference. Then we put in our inferential statistics. So we have the R and then the degrees of freedom. The degrees of freedom is also reported on the test here as 23. So we would write that as 23. Then we input our R value, which was 0.811. So we'll report that to 3 decimal places. 0.811. And then our p-value, which is p equals, or in this case we'll have to change it to less than 0.001. I'm just going to tidy that up a little bit to make sure that it's all looking okay and grammatically correct there. So finally, we have a Pearson's correlation revealed a very strong positive relationship between hand grip strength and forearm circumference. Then the inferential statistics, R value 0.811, degrees of freedom 23, P value less than 0.001 to support that statement. So that is how we do a Pearson's correlation, interpret it and write out the results. I'm now going to quickly show you what would happen if we violated one of those assumptions. So let's say we had a major outlier in our data. So let's say that someone had a freakishly, if I can say that word, high hand grip strength. So say they had hand grip data of 100. This is a person who only does hand grip training in the gym. And we can see that now we have that visible outlier and this test wouldn't be valid anymore. So what we would simply do is that if we violate the assumption, we uncheck the Pearson and we check the Spearmen, that's the non-parametric version, and we would essentially report the same inferential statistics. So you have the Spearmen's RHO this time instead of the Pearson's R, and then we have the degrees of freedom and then the P value itself. So very simple to do the non-parametric version there. Okay, I hope that was informative and I'll see you in the next one.